So welcome everyone to the Tech Brief session. I'm Daehyeok Kim. I'm a senior researcher at Microsoft. As we all know, P4 and programmable data planes enable us to express and implement custom data plane functionality. But there's a key missing pieces today, which is dynamic runtime reconfigurability. This is critical to support various dynamically changing workloads at runtime. So in this talk, Anjali Jain from Intel and Hari Thantry will be talking about one solution for this problem. Anjali and Hari, the floor is yours.
Thanks, Kim. Hi, this is Anjali from Intel along with Hari. We did come up with some use cases for providing P4 configurability at runtime, as Kim mentioned, and we came up with a solution or a proposal that we would like to share. We will take turns talking about both the proposal and the use cases. So why do we need this? We have a few use cases. One is supporting infrastructure use cases where we want to do certain machine profiles where you could provide template tables and a data plane that when you deploy it on a given machine for a use case like a cloud or wherever needed, you could do the last minute tuning of the tables to match the use case. And Hari will talk about one such use case, which is black holing via migration related. The other set of use cases are related to accelerating applications. And a key one is regarding the microservices where we have a last mile classification table, which might want to match on higher layers of protocols, L4 to L7, to identify maybe the connection in a different way, and maybe something that is not parsed by the hardware, but something that is deeper in the last parsed header or whatever. And this ability again is because it's the application that is deciding just when it is launched as to like what is the criteria for classification. It needs runtime hooks for doing the configuration for the table. The basic idea is that the compiler, when it is given a data plane, it contains some kind of a template of a table that helps decide the resource fitting for a given target. But then certain things we leave it flexibly for being defined just at init time before the table gets populated. And those are things like the key, instead of having a fixed match, you have something which is a selection of fields that you can use, or actions that are selectable, or the reason why this table will be visited, which is the preconditions, and you could have a selection of preconditions there as well. I'll hand it over to you.
Yeah, so like Anjali mentioned, the basic idea is that we have in the hardware, we have a physical table on which we would like to, at runtime, reconstruct a new pipeline. So overlay a different logical P4 table on that physical table. So, the way to do this at runtime would then be to say that there is a concept of a template table, which is a compiler directive that you see. And the template table defines the actual hardware table. So in this particular example, the template table would be a flow table. It contains certain attributes, and these attributes limit, add a constraint onto the logical table as to what the logical table must satisfy. So in this particular case, for instance, the flow table has attributes, in which case the unit is 16. So this would be key width, for instance. It says that first it specifies what units are being talked about. So this is 2 byte width, and in 2 bytes, the number of total width of that entry can only be 64 double words. The number of entries are 32 in the flow table, and the size is 384, which is 16K. In addition, we add an additional constraint where we upfront specify all of the actions. So this basically makes it easy for us uh, to not have to even construct these actions at runtime. So we believe this is a reasonable trade-off, because most of the time we know statically which how the actions must be executed, but we do not want to superimpose a logical P4 table during when we write the P4 program. So in this particular case, for instance, so the actions specifies a menu of actions from which one of n can be picked for any entry that is being added to a new logical table. And we specify a selector. So the concept of a selector actually becomes, you can understand, the selector specifies a precondition for lookup of this table. So by definition, a selector would consist of packet fields, metadata fields that can be set before this table is looked up. So at some point in the pipeline, if you want to insert a new P4 table, then the precondition, these fields contain the complete uh, uh, flags or metadata variables from which a conditional expression can be generated. So in the static flow, the P4 programmer would specify a template block. So so on the right side you see the template block, which is we specify that this particular code block is derived from the template flow table. There is a concept of an expression tag. The expression tag specifies the order of evaluation of these conditionals. So the lower numbers denoting the higher priority. So expression tag of 0 means this condition is to be evaluated first. And if this condition is satisfied, then the IPv4 table must be looked up. And in this example, the P4 author is already aware that at runtime he might want to insert a new table. So there is a gap between the expression tag. So expression tag of 0 as IPv4 lookup table, expression tag of 3 as L2 table. So now that the static program is compiled, at runtime, how do we insert a new logical table into this P4 pipeline? So we propose the addition of a new API, which we call P4 table insert, in which the arguments would be a P4 table name. The P4 table name is important because once inserted, this exposes the namespace for this P4 table to the P4 runtime API, and it can do CRUD operations on this P4 table. So first is the canonical name to allow for future CRUD operations on the table. Next is the template hardware table on which this P4 table must be mapped. This provides the compiler with information as to which particular underlying hardware table is being targeted. There is a conditional expression, and this conditional expression must only include conditions derived from the selector arguments that were specified in the program before. And runtime validation of this is performed to make sure that this conditional expression only comes from the selector variables that were included in the static program. The expression tag determines the order of evaluation. So in this particular case, for instance, it can take values 1 or 2. This allows it to be evaluated before evaluation of the condition for L2 table. And then there's a list of packet or metadata fields with mask. So this forms the key. Now note that the width of all of the packet and metadata fields must be less than the absolute largest width that the template table can support. Again, allowed actions are subsetted from the set of actions allowed on the template table. The default action is the default action that should be executed for this logical P4 table in the event of a miss. And then there is a list of default action args, which is if necessary. And then size determines the size of the table. So the corollary to that is the P4 table remove, where you just supply the P4 table, and this frees up all the resources for this P4 table. So with this basic infrastructure, let's get to the black holing use case. So what is black holing? So during times of VM migration, we would like uh, in our infrastructure to drop all packets that are emanating from the VM. This term we specify as black holing, and we would like this operation to be really fast. Uh, so in so so normally in our pipeline we derive something known as a packet type. So the packet type is the parse path of a packet in the P4 program, and every packet type is allocated to a group. In normal conditions, this allows us to flexibly have a mapping from groups of packet types into certain packet type groups on which then policies can be applied. But during black holing, we would like for all the packets emanating from VMs to be dropped. And one way to enforce that is to push them into a temporary group uh, and then have for that group have a default action of drop. So in hardware, there is a table, assume that there is a table called packet type group. Um, and the attribute of that is basically the packet type, because you basically are taking a packet type and you're creating an opaque value for this. So there are only two actions associated with packet type group table. One is you can set the packet type group, or of course, usually it's only set packet type group, but to motivate this example and also adding a drop action. And the selector for this is the local metadata p type, which was derived from the parse graph. So the P4 code section, static P4 code section for this has, again, two conditionals. In this example, we have an expression tag of 2, where if it's a non-fragmented IPv4 packet, then we do a v4 group table. Otherwise, we do a v6 group table. So now at runtime, we would like to drop all the packets during VM migration. So in this use case, we want to insert a new table as part of the same control flow, right? So we can do this by inserting this new logical table into the existing P4 profile, right? So we are inserting a new table. We call it the black hole table. It's overlaid on top of the packet type group table, and the condition that the that this table must be in the expression for this table type is if you look at the way the expression is specified, it's basically a postfix notation where we're saying, oh, if the packet type uh, masked with a 0 hex 0 equals 0 hex 0, then uh, you should exercise this code path, right? So this condition is evaluated and it's inserted at the highest priority, that is priority 0, and the key being looked up is local metadata.packet type. The list of actions is drop for this table. The default action is drop, and so this force, once this call is executed, every packet belonging to any packet type is dropped, because this is the first action this is the first expression that is evaluated. So after the control plane has migrated away all the VMs, the control plane can remove this table and can resume normal operation. So we remove the black hole table. Note that this example is somewhat contrived, but this illustrates the basic idea.
Yeah, thanks, Harit. So I would just very quickly go over another use case, which is, in this case, what we are looking at is we again have a template table. The flexibility we want is in the match key. And here, even though I'm calling this a selector, it is more like a match selector at the bottom, which says what are the fields that can be there as a match key. And the user at any time can decide, okay, I want to just match on say IP source or port test or some word 32 from the the TCP header or whatever. So it's a very very simple example where application wants to forward certain flows to a given queue. So the action is set application queue, and basically based on the user config data. Here, what I mean is a application coordinating with a P4 runtime server and saying, hey, I would like to create a table which matches only on 2 tuples or 3 tuples, of this, and here are the tuples that I would want to match on, and that's what is kind of being shown on the right side, where we say apply this table, the two-tuple table, or the three-tuple table, depending on what match criteria the so would like to. So in this case, applications of the config at runtime, again, very similar to what Hari mentioned. You would have to add the table with the right match specified in a similar manner that the format of which Hari listed, and move the table. Along with this, we would also want to have some kind of a query to know what is the template of the table, so you know what are the possible menu options for the matches that application can select from, and in that case, then decide what makes up with the best match for its usage. Right. So that's pretty much it. The result could be that you, as I said, forward to a particular application queue or something, or provide a hint to the application as a result of this match.
So yeah, this is very interesting idea. Thanks for your talk, Hari and Anjali. So I have a quick question about about this approach in general. So is this approach applicable to any P4 backend, such as like Tofino or IPU, or does it need some hardware support?
Let me try and answer this one, Hari. So yeah, I believe it applies to all backends, at least the ones that I'm working on from Intel side. Both to Tofino and to the Mount Evans IPU that we released, as well as FPGA or soft backends, right? It is more, the idea is here that when we are compiling, you have to have enough information that you would get a resource fitting for what you're building, but then leave enough flexibility for some init time or dynamic changes that may happen because of your deployment for a given server or application. Yeah.
I see. Yeah, thanks for your answer. And one quick related question is, how long does it take to reconfigure the tables? Like, is there any downtime during the reconfiguration, or is it just transparently happen?
This is not, we're not, so first of all, there's no recompile, right? We did a compile with the template, and then we asked or remove the table. Of course, there's, very tiny fraction of time that is used. The most important part is you have to do it in the order in which, when you are creating this table, you are, adding, you're enabling flows in a way that your first table is added at the end, right? So if you're multiple tables that you're defining, you always have to say the last table that you hit is added first, and the first table is added last, so that you get a consistent view of the pipeline. And you add table before you populate, of course. So it is almost always at init time, not so much at
Makes sense. And one last question I had is that it seems in the current version or current proposal, it seems to support match action tables, but could it be could this approach be extended to support like stateful objects, such as like P4 registers or any other stateful objects?
So, so far our use cases have been only to add match action tables. I think adding P4 registers, so P4 registers by definition are stateful, which means that they carry state from a prior operation. They may carry state from a prior operation. So virtualizing these kind of registers is a harder task, because there are not n copies that exist. There are not n copies that can be mapped onto a piece of hardware. So the answer is, at this point, is no. The way the proposal is constructed, it assumes that this would be mapping onto a piece of silicon which does not currently carry any state. So there's no save restore involved.
Makes sense. Okay.